Okay, we're going to dive into another little limit trick in this last section of lesson 7.3. And so it's all going to be based around our parent function for the reciprocal function that we learned, goodness, at the very beginning of the year. So we use the reciprocal function in this case because there's kind of some special details, characteristics about the reciprocal function as far as limits go. So when you look at this graph, if I say what is the limit as x approaches infinity, that would be like asking you to follow the right side of the graph and tell where it's leveling off. And this is leveling off at 0, right? It's never going to hit 0, but it's getting closer and closer to it. The same thing goes for the left side. If I say what's the limit as x goes to negative infinity, it's also 0 because it is also leveling off at 0, meaning getting really close to that value but never touching that point. So we use this trick or this concept that as you go to infinity or negative infinity on the reciprocal function, you're always going to approach 0 just by the nature of the way the graph looks. There's also two other characteristics down here listed that say, if you're going to 0, take the limit as x goes to 0 from the right side or the left side. They are both going to approach infinity, but on one side you're going to approach negative infinity. Also an interesting concept. So basically just this graph has a lot of like symmetry to it. So the limits have things that are similar from regardless of which direction you're coming from. So this is actually, this characteristic listed in number 1 and number 2 is actually something called what we call the stick of gum rule. And we call it the stick of gum rule because the idea is this. You're taking, let me get a little extra room. The idea is we're going to pretend like we aren't looking at the graph anymore. Instead, we're going to think about mathematically, what does this mean? Okay, so if I say take the limit as x approaches infinity for this function, in your head, the way you would do that is you would be thinking about what would happen to 1 over x when I put really big numbers in place of x, right? So what if I put in 100? What would that equal? 0.001. Okay, what if I put in 1,000 for x? 0.0001? Nope, that's wrong. 0.01, 0.001. You get the point. Anyway, what would happen is the larger the number on the bottom, let's just say it's like this, the smaller the value, right? So this is like a really small number, very close to 0. Okay, so we call this the stick of gum rule because it's kind of like if you take one stick of gum and you divide it an infinite number of times. So if I say I have one stick of gum and I'm going to tear this one piece of gum up and give a piece of gum to every person in the state of Ohio, would everybody have a piece of gum? Yes. Would you even be able to tell that they had a piece of gum? No. Meaning you are taking a piece of gum and you're dividing it, but you virtually have no gum distributed among each person because it's almost non-existent. It's so small. You could also say it like this. 1 divided by a really big number is going to equal a really, really, really small number. And the bigger x becomes, the smaller the answer becomes. So when we're taking a limit, we're generalizing. We're saying that 1 divided by an infinitely large number is going to equal an infinitely small number, aka 0. Okay, so we're going to use this concept to help us dig into some of these more complicated rational functions. I do want to point out that in each of these questions, our limit is going to be approaching infinity or negative infinity. So this does not be a situation where we could do the plug and chug technique like we have been doing, okay? Instead, what we're going to do is we are going to use a variation of the stick of gum rule. And in the directions you're going to see, or in this little note up here, it's going to say, to find the limits at infinity, divide each term in a rational expression by the highest degree term of x, and use the four statements above. The four statements were on the last slide. Here's what I'm going to tell you to do. Instead of dividing each term, what we're going to do is we're going to multiply each side of our function by 1 over x squared. By the way, that is legal algebraically because I did the same thing on the top and the bottom. Also, I chose x squared because that was the largest degree on the bottom of my function. So what would happen is you would still have your limit over here, but then you would have each of your terms would be written as over x squared. So 5x squared over x squared minus 3x over x squared, okay? Here's the reason we're doing this. We're doing this because our goal is to try to get something that we can like figure out based on things we know about limits. And one of the things we know about limits is that the limit as x goes to infinity for 1 over x is 0. So what we're doing is we're using a variation of 1 over x, in this case 1 over x squared, close enough, to try to manipulate our function to something that we can actually interpret. Okay, so I'm going to I put everything over x squared. Now I'm going to simplify, this is basic simplification, one fraction at a time. Okay, so if I said, what's 5x squared over x squared? Well, the x squareds would cancel, right? And that means you would just have a 5. 3x over x squared would be equivalent to 3 over x because one of your x's would cancel from the top and 1x from the bottom. 8 over x squared does not simplify, so it would remain the same. Okay, so just keep going through and simplifying one fraction at a time on the top and the bottom. Okay, we do have a lot of limit rules that help us break these larger functions down into smaller pieces. We learned that in 7.2. And one of those rules said that there was like a sum and difference rule where if you have a plus or a minus or a multiplication or division, you can basically take the limit of one thing at a time and then like add them all up or subtract or whatever the function is doing. And that's what we're doing here. So what I'm going to ask you to do next is take the limit one section at a time. I'm not going to write it out like that because it's going to take me forever if I do that. Instead, I'm just going to kind of write my answer as I go. So what would be the limit as x goes to infinity of 5? Well, that would just be 5 because that's like a flat line that doesn't move. The limit as x goes to infinity for 3 over x. 3 over x is a like sister function of 1 over x. That's that reciprocal function. So if 1 over x is going to equal 0 as we go to infinity, guess what 3 over x is going to do? It's also going to go to 0. So that's going to basically be like, why did I write 3? Oh my lord. 0 is going to be like 0. 8 over x squared is also like a cousin to 1 over x. So what did we say that the limit would be for 1 over x as we go to infinity? It's 0. So what's going to be the limit of 8 over x squared? 0. Because basically, again, it's that concept of you're putting a really big number on the bottom and squaring it, which makes it even bigger, and then saying, like, what's 8 divided by this giant number? It's a teeny tiny number that's essentially 0. Okay? So 0 again. And we're just going to keep doing this. We're going to keep seeing what happens if we arbitrarily plug in infinity. So again, 1 over x, the limit of that is 0 because 1 divided by a really big number is almost nothing. And then same thing here, 4 divided by a really large number is going to be almost 0. And so you're just going to clean this up and you're going to have a limit. So you're going to say the top would be 5 and the bottom would be 2. And that means that your limit is 5 over 2. Okay, that's a lot. I know it's like, very confusing at first. Just kind of stick with me. I'm going to go through, I think, 2 more examples. So we're going to do the same thing again. I'm doing this, by the way, because I can't plug in infinity the way that it is currently written. So I'm going to do 1 over x cubed for this question, and I'm using x cubed because it's the largest power on the bottom. Okay, honestly, these just kind of are tedious because it takes a long time to write out everything. I feel like once you see a few examples, they're actually very simple to solve. But again, it's that like testing your patience. It's taking forever to sit and write out all the steps when it's really not that complicated. So we're going through and we're taking each term and we're dividing it by x cubed. And once I get all of this written out, I'm going to simplify. Of course, if you feel like this step is unnecessary because you can already simplify in your head, go straight to that step. Okay, so you may not need to write this all out and then simplify. You might be able to do it, just going straight to simplification, and that's fine. So if I simplify, I'd have 3 over x plus 4 over x squared minus 5 over x cubed. And then the bottom would be a 4 minus 2 over x squared plus 1 over x cubed. All right, now we're going to take the limit. Remember, basically, if you have a regular number on top and a variable on the bottom, and you're plugging in infinity, they're going to get 0. Okay? So this is going to go to 0. 3 divided by a really big number is 0. 4 divided by a really big number is 0. 5 divided by a really big number is 0. So right now I have 0 plus 0 minus 0. Okay, on the bottom I have 4. 2 divided by a really big number is 0. 1 divided by a really big number is 0. So on the bottom I have 4 minus 0 plus 0. Okay, keep going. You do get a 0 in part of your answer, but that 0 is in the numerator, so you are able to safely say that you can get an answer because 0 divided by 4 is something that you're allowed to do mathematically. The answer just is a 0. Okay? Is it the same question twice? That's the same question twice. Okay. There we go. Last one. So we're going to do the same thing. We're going to use the variable on the bottom as our driving factor. So we're going to say, let's multiply by 1 over x squared. Okay, let's write it all out. I think I'll skip that middle step this time and just go ahead and say, I know it's going to be this over x squared. Like, what would that be? That would be what, 8x plus 5x over x squared would be 5 over x, and then 7 over x squared. The bottom would be x squared over x squared, that's 1. 5x over x squared would be 5 over x, and then 6 over x squared. So I'm going to go through and I'm going to look for when I'm dividing by infinity, and I'm going to make those a 0. 5 over x means 5 divided by infinity, that's 0. Here's another 0. Anytime you have an x on the bottom with a whole number on the top, it's 0 because we're going to infinity. Okay, so what do I have left? I have 8x over 1. Okay, this is weird because in the last 2 examples, x's have just completely disappeared in the step where we multiply by 1 over x squared. That didn't happen here. It's okay. What you're going to do now is you're going to do an arbitrary plug and chug with infinity. Okay, so you're going to say, if I am doing 8 times infinity divided by 1, what would you say that equals? It would equal infinity, right? Because you divide by 1, that doesn't change anything. 8 times infinity is basically infinity, so you have a limit that is equal to infinity. By the way, sometimes when limits equal infinity, sometimes you'll see them written as D and E. Just kind of use both depending on which format you're using.